Okay, I think trying to do some editing here on this video. Question number 5 says a mole of Einsteins. That's a mole of photons, rather, is called an Einstein. And we have 3 Einsteins, which means 3 moles of photons. And we want the energy. So energy is equal to H times nu times number of moles times Avogadro's number. You can also say that this is equal to Hc over lambda times number of moles times Avogadro's number. So when you do this one, you're going to say, okay, I've got 3 moles, 3 moles times 3 moles of photons times 6.02 times 10 to the 23rd photons per mole times, let me see here. I want to get my wavelength. I want to get my frequency. First of all, let me put Planck's constant in here. 6.626 times 10 to the 23rd. Oh, I'm sorry, 6.626 times 10 to the negative 34. I'm telling you, I'm not doing well this morning here. Getting too excited about chicken wings later. That's joules times second. And then my frequency is going to be, remember, frequency is equal to speed of light over lambda. That's 500 nanometers. So my frequency, when I go ahead and do that, is going to be 6 times 10 to the 14th per second, or also called hertz. That's the unit of frequency. So multiplying all these together, give me a second. That can't be right. Give me one second here. I think I put something in the calculator wrong. I always do these questions twice, just to make sure. Do the calculations twice. I know it's very exciting to listen to me hit buttons on a calculator. And I get an energy. I'm going to write what I get on the calculator. No, we don't want to do that. I'm going to write what I get on the calculator, and then we'll round it. 717,993 joules per mole of photon, for joules per 3 moles of photons. So let me see here. 1, 2, 3. So about 718 kilojoules in those 3 Einsteins of photons. All right, the rest of these with electron configuration stuff we'll go over in class. I just wanted to show you the calculations part. So I'm going to switch over to question 22. An X-ray, another type of electromagnetic radiation, has wavelength of 5 times 10 to the minus 10 meters. Calculate the frequency. Well, what's new? Hey, C over lambda. And I'm told that the lambda here, let me put the speed of light in here. We're told that the wavelength is 5 times 10 to the minus 10 meters. So that's an easy one to do. So if we just want to think about that, we can say that's going to be 0.6. I'm just dividing 3 by 5. It's 0.6 times 10 to the, well, I'm going to subtract. So that's going to be the 18th. And that's going to be hertz. Now let's change the scientific notation. I make this bigger by a power of 10. I have to make that smaller by a power of 10. There's my frequency of my X-ray photon. Okay, If an electron in the hydrogen atom goes from the n equal 4 to n equal 2, what is the wavelength of light emitted? Well, remember, this is question 23, by the way. That's a goofy looking 7. Let me get rid of that. 10 to the 7. And that's a constant called the Rydberg constant. 1 over n squared lower minus 1 over n squared upper. And we know that the lower energy level here, so let's rewrite this. 1 over lambda is equal to 1.097 times 10 to the 7 times 1 over 2 squared minus 1 over 4 squared. So doing that, now remember, you're going to get 1 over lambda. Incidentally, 1 over lambda is called the wave number. It's given that symbol. And a wave number, you'll probably not have to worry about this unless you're going to be a spectroscopist or a chemist. A wave number is another way of representing things in chemistry and physics. So 1.097 times 10 to the 7th parentheses times parentheses 1/4 minus 1/16. So that's going to be 1/4 minus 1/16. 1/4 is 4/16 minus 1/16. So that's going to be 3/16. So 1 over lambda is 205.6875 meters to the minus 1. I'm going to reciprocate that. And you get lambda is 4.86 times 10 to the negative 7 meters, or 486 nanometers, which is certainly one of the lines in the Balmer series of lines, the visible lines in the hydrogen spectrum. Okay, last question. All right, we've got lithium atoms, and in order for us to remove 1 mole of electrons from 1 mole of lithium atoms, it takes 279.7 kilojoules. That's the ionization energy that it takes, of course, to ionize lithium to lithium plus 1. So what we have to do is we have to figure out what wavelength of light do we need for that. Well, first things first. We've got kilojoules. We want to change it to joules. So we multiply by 1,000. 279,700 joules. And that's what we want to do now, is we have to take that number and divide it by Avogadro's number. Okay, because we are talking about now, this is how many joules in 1 mole. We want to get joules per 1 atom. So we're going to go 6.02 times 10 to the 23rd. And that's going to be electrons per mole. And this is joules per mole. So let's go ahead. Let me go ahead and do that. 279,700 divided by Avogadro's number. And you get a small number because you're only talking about 1 electron being removed. 4.65 times 10 to the minus 19 joules. Okay. Now, energy is hc over lambda. So lambda is hc over E. Good. Let's do it. It's joule seconds times speed of light, all divided by that energy, 4.65 times 10 to the minus 19 joules. Okie dokie. Okay, 6.626 exponent negative 34 times speed of light. And I'm going to divide it by 4.65 and times 10 to the negative 19. And you end up getting this. You end up getting 4.27 times 10 to the negative 7 meters, or 427 nanometers. Okay, so that's it. And the rest of these, the qualitative ones we'll talk about tomorrow. I don't think I need to go through electron configurations, but if you have questions on it, certainly I'll answer them tomorrow. Thanks, guys. Enjoy the Super Bowl. All right, good morning. Good Sunday morning. Good Super Bowl Sunday morning. I have in my hands here a copy of the little evaluation that we're going to be doing. So let me get moving on this, at least some of it. And then if you have any questions, certainly tomorrow there's another chance to ask. So I'm going to try to see if I can get my computer to do something here. Let me see. Good, it works. Oh, well, there we go. Okay, go away. All right, so first of all, we know that light has a dual nature. It has a wave nature, okay, with wavelength, lambda, and it has frequency, and it has speed. And we relate these quantities, lambda times frequency, wavelength times frequency is equal to the speed. In this case, the speed c is the speed of light, and that's 2.997 times 10 to the 8 meters per second. So what we can do with that is we can use that relationship to solve for frequency if we have wavelength, or wavelength if we have frequency. You should be comfortable manipulating that very simple equation. So, like I said, question number one, dual nature, wave and particle. So you can also picture light as having this particle-like character as well. We call that a photon. And we can calculate the energy of a photon. That would be using the relationship E is equal to hc over lambda, or h times frequency, where h is Planck's constant, 6.626 times 10 to the negative 34 joule times second. So you have all your relationships right here. Remember that as we look at the electromagnetic spectrum, somewhere around 400-ish nanometers down to 700 nanometers. That's about it for visible. And we have the violet up here, the red down here, and at longer wavelengths, we have what's called the infrared, and up here, of course, the ultraviolet. And if we get to even higher and higher energies, or smaller and smaller wavelengths, as the case may be, you can even get to gamma radiation. And we have at longer wavelengths still, we've got microwaves, and we've got radio waves, etc. Please don't mind my bad handwriting on this. I'm trying to use this stylus on this laptop, and it's kind of difficult to make it look good. Okay, so let's look at question number 3. And question number 3 asks us to look at wave-like properties of particles. We can do both because we have a relationship that says the wavelength is equal to h over m times v, where this is actually called the de Broglie relationship. And again, h is Planck's constant, m is the mass in kilograms, and v the velocity. And this is kind of an interesting question. It says do an order of magnitude calculation. If you look at the hint there, it's really simple. If you just want to find out, which is a longer wavelength or shorter wavelength. But remember, particles that are very light and are moving at very high speeds, they do have reasonable wavelengths. For example, electrons moving at at very high speeds, or protons moving at very high speeds. But if you're talking about something like a person running, it's not going to be very noticeable. Of course, it's the wavelength is infinitesimally small, pretty much. So let me show you about it. What is an order of magnitude calculation? Order of magnitude calculation is you don't have to worry about getting exact numbers. So let's take a look here at the electron. That's going to be about 6. Well, we don't have to do an exact calculation, so let's just call that 10 to the negative 34 on top, because we're just trying to get approximate values. And it has a mass of 9.11 times 10 to the negative 31 kilograms. That's almost 10 times negative to the negative 31, or about 10 to the negative 30 approximately. And it's moving at about 10 to the 6 meters per second. So pretty much all we have to do here is just take a look at these exponents. Negative 34 minus a minus 30 is negative 4. And negative 4 divided by 10 to the 6 is going to be about 10 to the minus 10 meters, approximately. Now let's look at the kid falling off the chair. You've got once again, approximately 10 to the negative 34 in the numerator. Again, I'm just doing an approximation here. And he's 75 kilograms. So let's say he's roughly 100 kilograms, about 10 to the 2. And he's falling at 5 meters per second. Let's round that. We can just call it 10 because we're just rounding. We're just doing an order of magnitude. So in the denominator, we've got 10 to the 3rd, and in the numerator 10 to the minus 34th. So that's about equal approximately to negative 34 minus 3, about 10 to the negative 37 meters. And that's how you do an order of magnitude calculation. Okay, looking at question number 4, as the principal energy level increases, what about the distance from the electron to the nucleus? Well, again, let's think about our simple picture. We have a nucleus. We have the n equal 1, n equal 2, n equal 3, n equal 4, etc., etc. And so we can say the probability of finding an electron farther from the nucleus, farther away from the nucleus, is higher as you move toward higher energy.